Hello, and welcome to part 2 of the lectures for chapter 14. In this second video lecture, we're going to cover sections 14.2 and 14.3. Now, 14.2 is very much a follow-up on what the first video was all about, which is the topic of dark matter, as we can see right here in one of our topics. But we're just going to talk about it a little bit more, and in the context of, well, honestly, more evidence supporting dark matter, and specifically supporting one of the main theories of dark matter, which is that it is composed of weakly interacting massive particles of a type that have yet to be discovered. All right, so our goals for learning in this section, labeled Gravity versus Expansion, is what is the role of dark matter in galaxy formation, and what are the largest structures in the universe? And of course, how are those ideas related? So if we look at the universe from the models that we have developed, astronomers have developed by analyzing and surveying thousands upon thousands of galaxies, we know that very early in the history of the universe, so after the first 500 million years or half a billion years, the universe was much denser and more uniform than it is now. However, it was lumpy. We can see lumps starting to form already as whiter pockets. Those are kind of like hot, dense pockets of gas. Now that lumpy distribution just becomes more dramatic as we move forward in time to 2.2 billion years, 5.9 billion years, onward to 8.6 billion years, and now up to basically the present day at 13.7 billion years since the Big Bang. See, notice what happens. The universe, of course, is expanding. Its approximate size, instead of being 13 million light years across, is now a whopping 140 million light years across. But definitely notice how pockets that were dense have become denser, all right? So we had continual grouping of galaxies kind of pulling in towards each other, galaxies getting formed and reformed, colliding with each other certainly, and voids or regions with no galaxies being left behind, okay? So there's almost a tendril look, a clumpiness to the universe on the scale of distributions of galaxies. Now, these models are based off of projections for hundreds of millions of galaxies. So the individual calculations in a model like this. So what role does dark matter have to play in understanding that structure to the universe as a whole? Well, gravity of dark matter is what caused these early so-called protogalactic clouds to contract in the first place. There are processes today that involve gravitational contraction with gases that already have molecules in them, molecules that were created inside of the cores of stars. But before there were stars, there would have been no such heavy molecules to allow for the collapse of, gases into things like stars. So how did gases collapse in the first place? How did they form the black holes that seem to be a role or have a role in the primordial universe? How did they form the first stars? And those first stars showing up in these first galaxies, these primordial galaxies? Well, as far as models suggest, there would have been just as much outward pressure due to heat energy as inwards gravitational collapse, creating a gravitational pressure. So these galaxies would never have formed unless there had been more mass pushing them in. Where did that more mass come from? Well, dark matter. Matter that is massive but cannot radiate away heat. It has a certain density, as we'll talk about. Okay? So the idea is that these WIMPs, those are the theorized components of dark matter, they can't collapse to the center of galaxies, for example, because they don't radiate away their orbital energy. So unlike a gas formed of ordinary matter that can radiate energy away as light, because that's the whole point of ordinary matter, it interacts with light, both it can absorb light and it can emit light, and that can actually then cause a gas to continue to collapse, letting gravity continue to get the gas hotter and hotter, even so hot as to start fusion at the atomic nuclear scale. But that doesn't happen with dark matter as far as we know. All our models of dark matter suggest, and the very idea that it's dark suggests, that it doesn't interact with light, so it can't radiate away energy. So basically, we think it can't collapse. Now, it was integral in causing the collapse of ordinary matter within the huge envelopes of dark matter that we think exist around galaxies, but itself it never collapsed. In other words, there's no such thing as a dark matter galaxy. Dark matter is stuck in a perpetual state of having basically one density because it just can't collapse anymore. Now, it's incredibly pervasive. It makes up most of the matter in the universe, as we talked about, but it's just diffuse. Huge clouds, low density, surrounding galaxies, which really makes sense in the context of how we've talked about it, like in the previous video. We talked about it surrounding galaxies. Well, you might have wondered why. Why isn't it intertwined throughout the galaxy? Well, because it can't collapse under gravity. All right, it can a little bit, but then it would the molecules would bump into each other, and then they would push back against gravity. That's what all the models suggest. Again, we haven't confirmed what actually dark matter is composed of, so these are just our best understanding, okay? But it does make some sense. It also would further explain the difficulty in detecting dark matter, because if dark matter exists in huge envelopes around galaxies, and there wouldn't be that much of it inside of galaxies, so there wouldn't be that much, say, in our own solar system. So we already have something that's very difficult to detect because it very weakly interacts with other matter, and, well, it might just be very rare on top of that. So dark matter is still pulling things together today. If we look at huge groups of galaxies like this here, the local supercluster, there's the label right there, which our Milky Way is one tiny small part of, well, that supercluster is coming together today. The paths shown here indicate how the galaxies over time and their velocities are coming together, right? After correcting for Hubble's law, which tells us that all galaxies are moving away from us because the universe is expanding as a whole, we see that the motion in individual groups isn't as simple as saying all galaxies are moving away from us. In our local group, there's gravitational pulls that are localized, and that's causing the local galaxies to pull together, although all the tendrils as a whole are pulling apart, right? So the tendrils are becoming denser, brighter, but then they're all moving away from each other. All right, so that's what we see in our region of space, which would be true of any region or pocket of galaxies. The galaxies are coming together. And the best models of gravity suggest that effect would only be explained by significant additional mass, in other words, dark matter. All right? So the largest structures in the universe are these huge tendrils of galaxies that are billions of light years across. So the maps of galaxy positions reveal extremely large structures. Superclusters, like the one that we talked about that our own Milky Way is part of, and voids, which are the terms given to huge gaps between the galaxies. Gaps that are many millions, billions of light years across, right? Huge gaps with just nothing in them. All right, well, probably a lot of dark matter. Okay, so the models show that gravity of dark matter pulls mass into denser regions. The universe grows lumpier with time. All right, so there's going to be continual concentration of mass. The voids will never get filled. In fact, the voids, those are those volumes of space between galaxies, will just become larger. So the structures in the galaxy maps look very similar to the ones found in models in which dark matter is, well, created and composed of WIMPs, weakly interacting massive particles. So it is further evidence based on the calculations, based on what these particles will look like. But again, astronomers and scientists have yet to confirm they exist. So what have we learned? Well, first, let's ask the second question. What is the role of dark matter in galaxy formation? Well, it is that the gravity of dark matter seems to be what drew gas together in the first place. So very important. Otherwise, it doesn't seem like the first galaxies actually could have formed. Physics basically says galaxies could not have formed when they were only hydrogen and helium. So that's kind of in need of a better explanation. Dark matter saves the day in a sense, right? You can kind of see that dark matter plays a role of it explaining a lot of phenomenon that we see with no better explanation, okay? So this indicates the process of galaxy formation. What are the largest structures in the universe? Well, galaxies appear to be distributed in gigantic chains, right? Those tendrils and sheets that surround great voids where there are no galaxies, all right? And that composition, that look to the universe definitely matches up with our understanding of dark matter. And there's no other explanation other than there's a huge amount of leftover matter that just doesn't seem to interact with light and is essentially undetectable. So no matter how frustrating it is to keep hearing me say that scientists have no idea what dark matter is, nor seem to be able to confirm its existence, we still have so much behavior, so much observed behavior in the universe that can't be explained otherwise. So it's not like scientists are just coming up with dark matter for fun. There's just no better explanation. All right, well, in terms of things with no better explanation, let's talk about dark energy. What is the evidence for dark energy? Because it's important to distinguish between dark matter and dark energy. They really are nothing alike. The term dark here is really just given to the sense that it is mysterious or not very well understood. In dark matter, the word implies that as well, but also can be taken more literally because numerous times I mentioned with dark matter, it is literally dark. It doesn't interact with light, any type of light, visible or otherwise, right? At least that's what the model suggests. So the two names kind of almost serve different purposes, but they also are chosen to group the two together because we don't have a definite understanding of either. All right. Now, maybe once we know exactly what dark matter is, we'll start to call it limp matter or something. And, maybe that will be distinguished from dark energy, even though, of course, it still does remain non-interacting of light. But to get off topic, we need to talk here about dark energy. And what are our goals in our discussion of dark energy? Well, we want to talk about what is the evidence for an accelerating expansion. An expansion of what? The universe as a whole, expanding since the very beginning, since the Big Bang, since the universe was a single point. Why is flat geometry evidence for dark energy? And what is the fate of the universe? So if we look at white dwarf supernova, we can see, and that's the curve here, we can see that the data collected of many white dwarf supernova and their velocities suggest a certain rate of expansion for the universe. And what is that rate? Well, let's look. So the four colored lines represent models of the four possible expansion patterns for the size of the universe over time. All right, so there are different potential models here, and it's good to compare between models, otherwise you never know if your model is correct. The different models involve an accelerating universe, okay? Hint, that's the one that the data points to. But the other possible models are a coasting universe. That would be a universe that is expanding but at a constant velocity. A universe that is reaching critical density, all right? So is gradually slowing down in its expansion, not coasting, but not accelerating either. And then one that is on the cusp of recollapsing. It's like an oscillator or a spring, and the universe will reach a maximum distance, but gravity will pull it back together, and it will recollapse into another single point just as it started. It will return to that state of the Big Bang, okay? This is the current moment in the history of the universe right now at about 14 billion years since the Big Bang, okay? So when we look at supernova, we are looking often back in time because as we look at further away galaxies, we have look back time, which is why many of these data points fall on points of time that are not the current, because we've essentially looked back in time as we've observed these supernovas. Now, white dwarf supernovas are a type of standard candle and a very important part of the distance ladder of how astronomers measure actual distances to objects in space. But in addition to the supernovas being such a good, white dwarf supernovas, being such a good standard candle, they also have told us about the expansion of the universe. Because we've collected the data of so many of them, scientists have, we've seen that yes, they're all moving away from us, which is consistent with Hubble's law, consistent with the concept of the Big Bang, but ones that are further away aren't moving away as fast as ones that are closer. And that tells us that, well, not as fast as we would expect, that tells us that as we look at newer ones, right, with less look back time, for example, only 4 billion years as opposed to a look back time of about 8 billion years, as we look at these ones that are, closer to our age in terms of since the Big Bang, well, those ones are moving faster. Why? What could explain that? The only thing that can explain it is that the universe is accelerating in its expansion. All right, it's speeding up over time. Everything's getting further and further apart. All right, so the fate of the universe depends on the abundance of matter and this mysterious thing, dark energy, which we'll talk about more. Here are the same models, but instead of shown on a graph of average distance between galaxies versus time, instead it's shown as pictures with the current, the present, the now being right along the midline, and looking back in time in each case to the Big Bang, shown as the kind of the starburst, and we can see the different types of universe, right? A recollapsing universe, a critical universe, a coasting universe, okay? So notice the critical universe just reaches a certain size. It just levels off, all right? The coasting universe, and finally, the one that is actually correct, although it's so strange, the accelerating universe. Notice in the accelerating universe, everything gets further and further away from it from everything else, right, the distance between galaxies just continue to grow. Now, is that like saying that voids are growing? Not quite, and I'll come back to that. So suppose that the universe has more dark matter than we think there is today. Dark matter. How would this change the age we estimate for the expansion rate? Well, the estimated age would be smaller, all right? Because that would, there would be less matter to explain where we're at in the history of the universe, okay? Now, the brightness of distant white dwarf supernovas tells us how much the universe has expanded since they exploded, okay? And these are the characteristic patterns of these white dwarf supernova that all have a particular true luminosity, which is how we can use them as standard candles. All right. So an accelerating universe, as I've said a few times now, is the best fit for that supernova data. Okay. So there's this really compelling data that the universe is accelerating in its expansion. However, to accelerate takes a force. When a force acts on an object, that's what we call in physics work being done. Well, work is a form of energy, or there's a relationship between work and energy. So that means that it would, in other words, take energy to accelerate the universe. Where does that energy come from? Well, it has to come from somewhere, and scientists suspect that there's just a leftover amount of energy that seems to permeate the universe, not as matter, but just as pure energy. And that is what's driving the acceleration. And the amount of energy necessary to drive an acceleration of hundreds of billions of galaxies is a huge amount of energy. And it ends up being that energy, according to E equals mc squared, is a much greater proportion of the total mass energy continuum of the entire universe than anything else. It makes up 68% of the universe. In comparison, dark matter makes up 27% of the universe, and ordinary matter makes up only 5% of the universe. Unbelievable, right? Unbelievable, right? So much of the universe is this completely not understood phenomenon known as dark energy. But we see an expanding universe and an accelerating universe. So what's going on? Well, measurements of the cosmic microwave background indicate the universe has a flat geometry. Thus, dark energy is needed to fill out the remaining mass energy. Okay? Otherwise, the geometry wouldn't be flat. The universe would be collapsing in on itself. There has to be something to almost like hold it up. Because if you think about space-time geometry, you should think about how gravity bends space-time. An idea that we've touched on a little bit in this class, but is a popular idea in science communication, that you can have these dents in the space-time continuum. And we even talked about how a black hole is essentially a hole in the space-time continuum. Well, if that's the case, if gravity bends and warps space-time, then gravity as a whole, driven by all the mass of the universe, should bend space-time in back over on itself. But that's not at all what we see, because such a geometry couldn't allow for acceleration of expansion. So that means the geometry has to be flat to allow for this acceleration. Well, that takes a whole lot of extra energy. That's where the dark energy comes in. Okay? So what is the fate of this flat universe that's accelerating in its expansion? Well, the eventual fate of the universe depends on the rate of the acceleration, which scientists are trying to pin down with more and more data. They just need to look at more of these white dwarf supernova and just have more ways of measuring the distances to different galaxies. If the universe does not end in a big rip, which is to say that space-time itself rips apart, it should keep expanding for a very long time, perhaps forever, right? We're just not sure. What is the universe? All matter will eventually end up as part of black holes, which will, if Stephen Hawking is right, eventually evaporate. So black holes can't last forever because they're not a closed system. They are losing energy, and so they're in the that appears to be the case. So if they're eventually losing energy, then you have a point where the whole universe will be at an equilibrium. Okay. There'll be a complete equilibrium. And if you wonder how are black holes losing energy, well, they're losing energy, for example, when they collide with each other and they create gravitational waves. Gravitational waves are a dissipation of energy coming from that black hole. And yes, it's true that black holes don't let light escape, but if they can create gravitational waves, they are radiating away energy. That definitely lends some credence to this idea that they will eventually evaporate, because once they run out of energy, they're just simply not there anymore. Now, why would everything become a black hole? Well, if the universe is accelerating in its expansion, everything is becoming further apart. Well, everything being on the whole. But we already talked about dark matter is still doing the job of pulling local clusters of galaxies together. That just means that their universe, will become more and more sparse tendrils. Those tendrils will eventually have collided with each other and basically given up all their heat through collisions of galaxies and stars until they're just all black holes. So that's the eventual fate of the universe. Chains of black holes that are slowly evaporating over, honestly, hundreds of billions or even trillions of years. So we are talking orders of magnitude longer than even the age of the current universe, which is already a huge number. So it's very speculative. So what have we learned? Well, what is the evidence for an accelerating expansion? What is the evidence for an accelerating expansion? It's measurements, okay, so direct data of distant white dwarf supernova, all right? And those indicate that the universe is expanding faster now than it was earlier. So we see a speeding up, that's the acceleration. Why is flat geometry evidence for dark energy? Well, the evidence from the cosmic microwave background indicates that the universe is very near critical density, requiring an additional contribution to the mass energy of the universe. And that's mass energy in the context of E equals mc squared. In other words, mass can become light, light can become mass. All right, so what is the fate of the universe? The universe should keep expanding indefinitely. The universe eventually consisting of a dilute sea of fundamental particles. All right, all in equilibrium, which is consistent with the second law of thermodynamics. The universe is approaching a state of maximum entropy, which is you see everything at the same low temperature in a maximally disordered state. But good thing is that won't happen anytime soon. Well, thank you so much for watching this lecture. I hope it has been interesting and informative.